Welcome everyone to this Monash Cybersecurity Seminar. Today we are honored to welcome Neal Koblitz from University of Washington in Seattle. Neal Koblitz received his PhD in mathematics from Princeton in 1974, and since 1979 he has been at the University of Washington in Seattle. He is a co-inventor of elliptical cryptography, which, as you might already know, is one of the most widely used cryptographic approaches. And for this, he received the RSA Award for Excellence in Mathematics, the Information System Security Association Hall of Fame, the Edward Rhine Foundation Technology Award, and the Levchin Prize in Real-World Cryptography. In recent years, most of his research has been devoted to analyzing and critiquing claims of provable security, which is also the topic for his talk today. And he will talk to us about analysis of the Ideal-SIVP to Ring-DLWE security reduction, which is again one of the most commonly used security basis claims for lattice-based cryptography. So thank you very much, Neal, and the scene is yours.
Okay, thank you very much. I'd like to thank the organizers for inviting me to speak at the Monash Cybersecurity Seminar. Very glad to be here virtually. So my topic is our analysis of the provable security claim for the decision Ring-DLWE problem, which some important cryptosystems are based on problems quite similar to it. So in recent years, cryptographic protocols based on the presumed difficulty of learning with errors problems in one form or another, different types of problems of that type, have found widespread application for key encapsulation mechanisms, for signatures, homomorphic encryption, attribute-based encryption, and sort of most interestingly, post-quantum cryptography. So of the 7 finalists in round 3 of the NIST competition for PQC standards, 3 of them, Kyber, Sabre, and Dilithium, were based on learning with errors or the similar learning with rounding problem. And just last year, the NSA gave its endorsement to LWE-based quantum safe protocols. So the outline of my talk is that first I want to briefly discuss how some of the things that have been said in support of lattice-based cryptography, basing their appeal very much on provable security claims. Perhaps more than any other type of crypto system, provable security claims have been at the heart of the case that's been made historically for lattice-based crypto. Now, then I will discuss 4 main problems we found, concentrating specifically on the security reduction in the paper that related decision ring LWE to short independent vector problem. The first is a restriction to cyclotomic ideal lattices. The second is the size of the approximation factor. The third is the tightness gap. And the fourth is a questionable quantum part in the security reduction algorithm. And then I'll make some general comments, some conclusions of a broad nature. This is joint work with Palash Sarkar, Indian Statistical Institute in Kolkata, and 2 other researchers from India, a postdoc of Palash's and a PhD student of his also collaborated with us on this. We analyzed the security reduction, or at least the main bulk of our papers devoted to an analysis of the security reduction in the 2013 paper by Vadim Lubashevsky, Chris Pikert, and Oded Regev. And I'll refer to this as LPR. That'll just be my abbreviation for it because I'll be discussing it a lot. That related the hardness of breaking a ring decision LWE problem, a crypto system based on that, to the hardness of approximate Ideal-SIVP, and I'll recall the definitions of those problems later. Much of their reduction closely followed an earlier paper by Regev, which gave a similar reduction for general lattices. And these are where the papers can be found. And I'll be happy to send these slides to the organizers later. And so these are the three authors of the paper. That's the main topic I'll be talking about. All of them have very extensively done research on lattice-based cryptography. So first part of my talk, ever since Ajtai Dwork's work in 1996 got things started over a quarter century ago, the central argument for security of lattice-based systems has been the, quote, provable security guarantees coming from worst case to average case reductions. Here are some quotations from people saying this, basically. Chris Pikert in 2015 said, worst case reductions give a hard and fast guarantee that the crypto system is at least as hard to break as the hardest instances of some underlying problem. This gives a true lower bound on security and prevents the kind of unexpected weaknesses that have so often been exposed in schemes that lack such reductions. A very strong statement. And then later on, in speaking specifically of ring learning with errors, he said that its worst case hardness, an extra bonus is its worst case hardness properly. Let me start again. An extra bonus of ring learning with errors is its worst case hardness. Properly parameterized, breaking it is at least as hard up to quantum poly time as finding short vectors in any ideal lattice in the ring, and perhaps harder. And then another paper that's also relevant to what I'll be saying by Langlois and Stellet in 2015, giving a very similar result for module learning with error, which is closely related to ring learning with error. And we also analyzed in our paper. And they said, but perhaps the most appealing aspect is that lattice-based cryptographic protocols often enjoy very strong security proofs based on the hardness of worst-case problems. And a comment by Lubashevsky was quite interesting. He was talking about using an efficient method in number theory to make things faster. And there were certain values of the modulus Q that were best, that were preferred. And he was very glad to find that in this line of research, that avoiding certain, perhaps potentially risky values of that modulus is really unnecessary, because the reduction, the security reduction, the worst case to average case reduction, don't care about the modulus Q. This was surprising to him, because apparently there were attacks on Entru, which of course is not that close to the LWE-based systems, but there was some worry that certain properties of the modulus Q could lead to attacks. And so there was a caution about using them. But he said, we don't have to worry about that because the proof goes through without taking those so-called precautions. And I would say that using a rationale like that for ignoring cautions about protocol design can be dangerous. There was a case many years ago when Hugo Krychek produced a variant on the MQV key agreement protocol, which was more efficient, in particular because it dropped a public key validation step because his proof didn't need it. And then it turned out that one of the protocols he designed that way was insecure. It's completely insecure, and there was a problem in the proof. So relying on a proof to take precedent over maybe your intuition about what might be an unsafe choice of parameters can be a very risky business. Anyway, so that was just some examples of statements made about putting a tremendous amount of faith in these security reductions. Okay, so just to recall the basic problems that I'll be referring to, the approximate shortest independent vectors problem with approximation factor gamma is the problem of finding a full set of n independent lattice vectors, where n is a dimension, whose longest vector is within a factor of gamma of the shortest possible value of the longest vector in such a set. And similarly, and the exact SIVP, of course, is the version when gamma is a special case when gamma equals 1. Similarly, SVP gamma is the approximate version of the shortest non-zero vector problem. Then LWE, in the general case, for an arbitrary lattice, is just a noisy linear algebra problem. So we can start out thinking of a linear system with matrix A having rows of n vectors. The rows of the matrix A are random n vectors over the integers mod q, and S is the secret column vector, n vector, also over the integers mod q, and then you perturb the right-hand side and create a vector of real numbers modulo q that's obtained from B by adding an error vector E chosen according to a Gaussian distribution of width R. So it's a perturbed or noisy linear algebra problem. So that's the general definition. And the LWE problem is finding the secret vector S, given the matrix A and the perturbed right-hand side B prime. Now, what we're mainly interested in is ring learning with error. For a given, we have a given fixed algebraic number field K of degree n with ring of integers R. K has a standard embedding into n-dimensional Euclidean space in which the ring R, or any ideal of R, any integer or fractional ideal of R, embeds as a lattice. Then instead of a random row of a matrix A, we take a random element small a of the ring of integers mod q. The secret S belongs to the dual ideal, the lattice of the dual ideal, denoted R sup V. Then instead of having a dot product of a row of the matrix, we have just multiplication. We can use multiplication in the field K, and the basic operation is A times S. So now the input is a set of samples of the form A comma B prime, where A is a random element of R of the ring of integers mod Q, and B prime here a little change is that they normalize by dividing by Q. So you don't just multiply the secret by A, you also multiply by 1 over Q. And so you're not working anymore modulo Q times R dual, but rather modulo R dual. And E is now, again, a vector in Euclidean space according to a Gaussian, chosen according to a Gaussian distribution. Okay, and finally, and again, the problem is defined S. And finally, in our list of problems is the decision version of Ring-LWE. They're the parameters of the modulus Q and the distribution with R. And that's the problem of distinguishing with non-negligible advantage, which will denote delta, between a set of Ring-LWE samples A, B prime, defined as in the previous definition of Ring-LWE, distinguishing between a set of Ring-LWE samples and a set of pairs A, B prime chosen uniformly at random from the same set as samples are chosen from. Okay, so now to get to part 2, I want to talk about some of the assumptions. So this was, recall this is a reduction from the, let me just go back, from SIVP gamma applied to cyclotomic ideal lattices, which are the ones for which they have a nice polynomial time reduction. And so from SIVP gamma restricted to cyclotomic ideal lattices, that can be reduced to decision ring LWE. Okay, so now in this reduction, in stating that this gives a good evidence of security, and there's several implicit assumptions. One is that the subproblem of SIVP restricted to ideal lattices, and in particular to cyclotomic ideal lattices, is as hard as unrestricted SIVP, or at least essentially as hard, or hard enough that it can be relied upon in the same way we would rely upon SIVP as an example of a mathematically difficult underlying problem. SIVP is known to be NP hard, and in fact, the approximate version, if the approximation factor is small, is also known to be NP hard. But that's the version for general lattices, and they're applying it to structured lattices. So the reason for skepticism about this implicit assumption, first of all, ideal lattices have a multiplicative structure as well as an additive structure. Every lattice is an additive group, but an ideal lattice must be stable under multiplication by any element of the ring of integers. Cyclotomic ideal lattices, which are what's recommended for efficient implementation, have even more symmetry. And here's just a simple example. The only two-dimensional ones that arise just look like tiling of the plane by equilateral triangles or squares. So short vector problems are absolutely trivial. You see at a glance where the short vectors are. Now, you could say, well, two-dimensional lattice problems are pretty easy anyway. In fact, they can be solved in polynomial time using basis reduction that essentially goes back to Gauss. But there's a difference in difficulty here. That's not a completely trivial matter. And in fact, in Michiancio and Goldwasser's book on lattice algorithms, they devote 8 pages to the Gauss algorithm and to proving that it's polynomial time. So already with 2 dimensions, we see what appears just intuitively to be a significant difference in difficulty of lattice problems for cyclotomic ideal lattices and general lattices. And I think it's reasonable to think that in higher dimensions that the difference in difficulty would be greater, although can't visualize this easily. And I'm not saying we can prove this certainly, but it's kind of hard to believe that the level of difficulty is really comparable before and after restricting to cyclotomic ideal lattices. And another example of a sort of distinction is that for cyclotomic ideal lattices, the SIVP gamma trivially reduces to SVP gamma. And that's just because if you have a short vector V, then you can get a full set of independent vectors of the same length by scalar multiplication by roots of unity. Now, in contrast, in a general lattice, the best known result for reducing SIVP to SVP is in an n-dimensional lattice, which is also proved in the book by Michiancio and Goldwasser, is that you can get the reduction, but you have to relax the approximation of SIVP by a factor of square root of n. So that suggests that in the general case, if that's the best result you can get, that suggests that SIVP, approximate SIVP is harder than approximate SVP with the same approximation factor in the general case, because you have to relax the SIVP to get the reduction. Whereas for cyclotomic fields, they're equivalent for the same level. So that shows that certainly suggests, I would think that the cyclotomic case, SIVP gamma is easier than in the general case. So you get this separation between the SIVP and SVP for general lattices, but not for cyclotomic ideal lattices. Also, Dan Bernstein and Tanya Lange have some preliminary attacks, what they call the S-unit attacks, using the number theory, and they also give a list of other attacks on of various sorts, varying degrees of seriousness. I want to mention that in the security section of the introduction to the paper, the LPR paper, the author stated that despite considerable effort, no significant progress in attacking these ideal lattice problems has been made. In other words, they were claiming that there's good reason to think they are hard, and presumably in the sense of not having any algorithms to attack them that are much better than the generic algorithms. At least that seems to be the implication of this statement. However, I don't think the italicized words are correct. That even now, 9 years later, it would be an exaggeration to say that approximate ideal SIVP has been extensively studied, and that we have a really good handle on how hard it is and what the best algorithms are. So why were they so interested in transitioning to ideal lattices, and especially subatomic ideal lattices, when these security questions can be raised about them? And the reason was efficiency. They wanted to make lattice-based cryptography competitive with other methods that would at first seem to be more efficient. And they described this reason in the introduction to the LPR paper. And they point out that that you get your relations, you get your samples more quickly in the Ring-DLWE than you do in the general LWE, and you end up with key sizes that are smaller. At least the public key is smaller by a factor of n. This is especially beneficial because key size has probably been the main barrier to practical lattice-based cryptosystems that enjoy rigorous security analysis. So it's really efficiency is the reason for going to this special class of lattices. The next assumption they make is that approximate SIVP with an approximation factor of intermediate size, namely the size that arises that's necessary to make their proof go through, is as hard as exact SIVP, or again, maybe not as hard, but not a whole lot easier. And there's reason for skepticism about this, and this gets to our work sort of trying to trace the details of the proof to find out what parameters they need. And we found that in order to make the proof go through, their approximation factor has to be at least n to the 7/4 times delta to the -1/2, where n is the dimension of the lattice and delta is the advantage of the distinguisher. That is, the distinguisher which would presumably compromise the security of the protocol, and delta is the maximum advantage you're willing to let it have. And this is just approximate. We're neglecting a log term here. Taking n to be 2 to the 10th, which is a common choice for the dimension. And then for delta, 2 to the minus beta, if you want to be very cautious, maybe beta would be the security parameter, say 128, or you might be satisfied with something smaller. Let's take 45, for example. Then we get delta is greater than 2 to the 40th. Okay, so just taking those as sort of reasonable values, we see that the fastest algorithm known for SVP gamma, and in the case of the subatomic ideal lattices, that's equivalent to SIVP gamma. So it will also apply to the problem that the security proof is based on. That has running time very roughly equal to 2 to the n over k. Say very roughly because there's also a log factor in the exponent, and we didn't try to get this more precise. But 2 to the n over k in this case is 2 to the 25th. So it's a useless lower bound on the problem. So this also suggests that for gamma of this magnitude, like 2 to the 40th, we're already outside the range where we can say its difficulty is comparable to exact SIVP. And just a parenthetical remark, there are also questions arise about the value of Q. To make the proof go through, Q would have to be large. We estimated with reasonable parameters, roughly 2 to the 35th, which is too large to be efficient. Nobody would want to use that. In Kyber, the recommended value of Q is roughly 2 to the 13th. Okay, another reason for skepticism about implicit assumption B about approximate as opposed to exact is that Goldreich and Goldwasser showed that if the approximation factor is greater than square root of n, then SVP gamma and also therefore SIVP gamma for cyclotomic ideal lattices is very unlikely to be NP hard. Namely, they proved that SVP gamma is then in the intersection of NP and co-AM, co-Arthur Merlin. So it's widely believed that it could not be NP hard. So that's another reason for skepticism. So another implicit assumption, and for this assumption, I'm going to assume for the sake of argument that the first two assumptions are valid, and in fact, the approximate SIVP for cyclotomic ideal lattices is exponentially hard. I gave some reasons why I don't think it is, but for the sake of examining their assumption C, let's suppose that they really are reducing from an exponentially hard problem. So then they assume, when they make these asymptotic proofs, that if the tightness gap between an exponentially hard problem and the problem of breaking the cryptosystem is polynomial, what they call polynomial looseness, then for cryptographic values of the parameters, we have a hard and fast guarantee that breaking the cryptosystem is infeasible. Now, the tightness gap, speaking informally in this case, basically means the number of times an oracle for the decision ring LWE problem has to be queried in order to solve the approximate ideal SIVP problem. It's how many times you have to run this supposed attack on your system in order to solve the hard problem. So the general outline of how this works, and this is standard practice-oriented provable security, that you suppose your hard problem, you reduce a hard problem to Q to the problem P of breaking a crypto system. And suppose that for reasonable parameters, the best algorithm known for the hard problem takes time T1, and the reduction has tightness gap G. Then we get a lower bound of T1 over G for the time required to solve P, based on the idea that if P could be solved more quickly than that, then it would give you an algorithm for Q that runs faster than the fastest known algorithm for Q, which is reasonable to assume it's not going to happen. So, so that's a general idea. And our approach in our analysis of the reduction is based on the whole philosophy of practice-oriented provable security that was popularized by Bellari and Ragoway in the 1990s. Well, the LPR reduction is an intricate sequence of 10 nested algorithms. It consists actually of 9 sub-reductions from one algorithm to the next. Some of these intermediate reductions are tight, but some of them are not. And then the tightness gap for the whole combined reduction is, of course, the product of the gaps at all the stages. And this is what makes it possible to get such huge value, to get huge values for tightness gaps in these sorts of reductions. Now, we closely followed the reductions outlined in the paper and translated polynomial looseness into concrete functions of the parameter. Now, our final results, slightly simplified, we dropped I dropped terms that are not major contributors to the tightness gap, has order Q n to the 20th, delta to the minus 10. And actually, Q is not a major contributor. It's really n to the 20th, delta to the minus 10. N is the dimension, delta is the advantage of the distinguisher. Using the parameter values I gave before, n equals 2 to the 10th, delta equals 2 to the minus 45th, we get a tightness gap. Well, if we drop Q, since it only would contribute, say, 2 to the 35th, if we use the Q that the proof requires, we might get a little more, but let's say 2 to the 650th rather than 2 to the 685th. Okay, now, so what's T1? Well, strictly speaking, because the reduction uses a quantum algorithm, we should choose the time to be the running time of the best quantum algorithm known for approximate ideal SIVP for our parameters. However, we don't really know what the best algorithm is. I mean, there's not enough experience with it to make a judgment about that. And in any case, I said I would assume, just for the sake of argument, that that this approximate ideal SIVP, even when attacked by a quantum algorithm, is every bit as hard as exact SIVP in the generic case against classical algorithms. Let's just assume that. So let's just take T1 to be a value that's undoubtedly a lot more than what it should be, namely the running time of the best classical algorithm for exact SIVP for general lattices, which is very roughly 2 to the n over 3, which in our case, when n is 1024, would be about 350. And then we obtain a meaningless lower bound for the time required for the cryptanalytic problem, about 2 to the negative 300. So the tightness gap is just huge here. Now we understood, I should say, when we did this analysis, we understood that Lubachevsky, Peikert, and Regev were only interested in an asymptotic result. So they didn't try to pin down any tightness gap or anything like that. They did not try to minimize the tightness gap. So we reworked their estimates and were able to improve a few of them. So for example, one of the stages reduces each component of a decision LWE problem having error distribution of unknown width with a known bound to the corresponding component of a version having distribution of a fixed known width. This caused a discrepancy between the two distributions that had to be accounted for and led to a big contribution to the tightness gap. And that involved a calculation using the Rényi divergence. If we followed their computations of the Rényi divergence, we would have obtained a tightness gap estimate for this step of roughly n cubed delta to the minus 2 cubed. But by just being a little bit more careful about the computations of the divergence, we were able to lower this to the 1/2 power of n cubed delta to the minus 2. So we did this where possible, but there wasn't a whole lot of improvement that we could make in their calculations. And the final implicit assumption they make is that a quantum computer can handle a nested sequence of algorithms as well as a classical computer. And I think we have to be careful about sort of thinking of a quantum computer as magic, or even thinking that anything a classical computer can do, a quantum computer can do better, because it's more complicated than that. Well, okay, so the LPR paper essentially repeats the quantum part of Regev's earlier paper. In that paper, Regev somewhat minimizes the role of the quantum part, saying that it's needed only in one step of the proof of the main theorem. Now, in a sense, that's correct. From an expository standpoint, there is no need to talk explicitly about quantum computation, except when describing the third of the nested algorithms. However, in another sense, the statement's misleading, since it turns out that all of the stages after that one, and in the LPR paper, there are 7 stages, 7 reductions after the one that kicks off the quantum part, must also be carried out on a quantum computer. Let me explain why. Well, of the 10 algorithms in the LPR paper, labeled A0 through A7, then D1, D2, the quantum part starts with A2, whose task is to solve a discrete Gaussian sampling problem with distribution width less than half the width of the distribution in an input sample. So basically, Gaussian distribution finding vectors near to the lattice according to a certain distribution. The A2 algorithm wants to narrow that distribution, make it more accurate around the lattice by a factor of 2. So the procedure is that it creates a quantum circuit and then a quantum state in a roughly 2 to the 3n squared dimensional Hilbert space. And remember, n's about 1,000, so this is about 2 to the 3 million. This would require, for n equals 2 to the 10th, this would require about 750 times as many logical qubits as Shor's algorithm would require to factor 2048-bit RSA modulus. So we're dealing with a very large quantum circuit here. Okay, so the key point in the algorithm, it gets a state that's a linear combination of roughly 2 to the 3n squared term, each involving 2 entangled registers. The algorithm needs to erase one of the registers. Basically, one of the registers has a lattice vector and the other register has a nearby real vector. And so it wants to erase the vector that has the lattice, that is, erase the vector to which the other one is the nearest vector. I meant to say that it wants to erase the lattice vector that's the nearest lattice vector to the other vector. So what it has to do is uncompute a closest vector. So if it didn't have the lattice vector, finding the closest lattice vector would be the closest vector problem, but it has to uncompute it, to disentangle the register. It has to uncompute the closest vector in the lattice. So to do that, the uncomputing is done by creating a quantum circuit that computes closest vectors using the ring decision LWE oracle, and then reversing that circuit in order to uncompute the closest vector. So the implication of that is that a quantum circuit for all of the 7 nested reductions from A2 to D2, that is all except for the first 2, must be incorporated after being reversed into the quantum computation. With reasonable parameters, the scale of the quantum circuit, the complexity of the quantum circuit, number of logical and physical qubits, the circuit depth, the number of Toffoli gates is at least several orders of magnitude greater than what would be needed for Shor's algorithm to break RSA 2048. And also notice, by the way, as far as the size of the quantum circuit goes, that if you tried to respond to the tightness gap by increasing n, which you could do, you'd have to increase n substantially, and that would, of course, reduce efficiency, but more seriously, it would also rapidly increase the scale of the quantum computation, since the number of qubits is quadratic in n. And I think even optimists wouldn't predict that there'd be quantum computers in the foreseeable future that are scaled to handle this huge of a quantum part of the reduction. But that's not, it seems to me, that's not the most serious problem with the quantum part. The most formidable obstacle is quantum decoherence, which results in the inability of a quantum computer to store data for a significant time period. And this, as I understand, is the major negative of a quantum computer compared to a classical computer. That local storage, which is trivial for a classical computer, is a big headache for quantum computation. Now, normally, if you can do complicated algorithms that have certain type of storage needs on a quantum computer, but what you do is break them up into a sequence of sub-algorithms, each producing intermediate output to use in the next stage. That output can be read by a classical computer, which also rewires a quantum circuit, prepares it for the next stage, and so on. And apparently you can do quite complicated things this way. This means that interaction with the classical computer is essential in that type of complicated algorithm, which, by the way, doesn't happen in Shor's algorithm. Shor's algorithm is extremely simple by comparison with what we're talking about here. There's no need for interaction with the classical computer in Shor. In the definitive book on quantum computation by Nielsen and Chuang, they write that, quote, the cost of the classical computations and communication that are done during state preparation, syndrome measurement, and recovery could potentially be quite high. And they are talking about complicated algorithms. They're not talking about Shor's. But a quantum state cannot be stored somewhere while this interaction with the classical computer is happening. It cannot be conveyed from one state to the next, cannot be preserved, certainly on a classical computer. We're talking about a 2 to the 300 million, a 2 to the 3 million dimensional Hilbert space. Well, so in the LPR reduction, the quantum state constructed by the A2 algorithm, which is a linear combination of 2 to the 3 to the n squared terms, each with 2 entangled registers, needs to be preserved until the closest vector uncomputing is complete, because that has to be applied to each of those 2 to the 3 n squared components. There are also issues of 4 of the 7 algorithms inside the quantum part. Also require us to preserve intermediate output that gets used as a later step in the algorithm. If each of these were a standalone algorithm, this would be possible through interaction with the classical computer. So those algorithms individually are not all that complicated and could be carried out with the help of a classical computer. But we don't see how this could be possible if the algorithms are all nested inside of a master algorithm that's being applied to a fixed quantum state. So that's really the issue. Now, we do mention some caveats because none of us are experts in quantum computation. And what's more, any discussion of what large-scale quantum computers can and cannot do is necessarily speculative, since they don't exist at present. And the physics and engineering knowledge about them seems to be at a very early stage, as exemplified by the experiment 3 years ago that had an 86% failure rate applying Shor's algorithm to factor 35. Okay, and we are making some assumptions, such as we don't fully understand what the reverse circuit's going to look like. And we're just assuming that the same issues about temporary, local storage and preserving things and quantum decoherence that would apply to the nearest vector algorithm would also carry over to the reverse circuit. We're just assuming that's a reasonable assumption, but we're not experts in that at all. Commenting on how all of these doubts about the practical, or more than doubts, it's pretty obvious that there's no practical value in the security reduction from the standpoint of practice-oriented provable security. Now, how does this bear on the NIST Round 3 PQC finalists? 3 of the 7 are based on problems that are not the ring problem exactly, but a hybrid between the general lattices and ideal lattices. But they're much closer to the ideal lattices than to the general lattices. What's going on there in these module LWE problems is the lattice dimension n is of the form m times d, where m is the degree of the number field and d is the rank of a module over that, over the ring of integers of the number field. The cases that were studied in these 2 papers by Regev and LPR are the cases, Regev studied the case when d equals n, that is m is 1, the number field is rationals, and you have a general lattice, and LPR is the case d equals 1, where you have m is n, the degree of the number field is the dimension of the lattice. Now, in the 3 finalists, Kyber, Saber, and dilithium, d is taken to be 2, 3, or 4. So that's why I say that it's closer to the case d equals 1 by far than to the case d equals n. So it's what we call a structured lattice, even though it's not quite as structured as the case of a purely ideal lattice. And in Saber, I should also mention that Saber uses the module with rounding rather than the module with error, with a Gaussian error. I don't think that people think that should make a big difference as far as security goes. Okay, so finally, my conclusions. First of all, there's no rigorous mathematical argument that supports security of ring decision LWE-based crypto systems. Not that we're saying they're insecure. We're certainly not saying we know that. It just means that to have confidence in their security, one has to let them stand the test of time and show their resilience against attempts to attack them. That the security reductions by themselves don't give us any reason to have confidence in their security. More generally, I think that that proof of security, provable security are terrible terms to use, basically because they're oxymorons. There's no such thing And contrary to what Pikert claims, in our field, there are no hard and fast guarantees of security. The commonly understood meaning of proof is reflected in what Wikipedia says. Proofs are examples of exhaustive deductive reasoning which establish logical certainty to be distinguished from empirical arguments or non-exhaustive inductive reasoning which establish reasonable expectations. So to the average person, mathematical proof means something like the proof of the Pythagorean theorem you might have seen in high school geometry class. And to most people, to question the result of something that's mathematically proved is as foolish as questioning the Pythagorean theorem. Now, within our own research culture, we might understand perfectly well that a proof of security is not a proof in this mathematical sense, but something much less, something qualified or contingent, conditional on strong assumptions that might possibly not hold. But the use of the term proof of security or proof of security when we write for the general public or for anybody outside our own research subculture is misleading and deceptive. I think there are many areas. Cryptography is by no means alone in seeing the value of mathematics as essentially a weapon. And there are books about this, like a wonderful book by Cathy O'Neal called Weapons of Math Destruction, about a totally different subject, namely the abuse of algorithms in data science. And there's also a great book by Susan Landau about automated contact tracing and how sort of the math has failed there, in her view. So it's a widespread issue, in my opinion. The problem is that mathematical arguments, whether they're valid or fallacious, make a strong impression on people, especially those who do not have advanced mathematical training. And for most people, it is difficult to question the results or think critically about something that's being claimed if everything's cloaked in mathematics. Now, even within our community, although we do understand what proof of security means, the use of excessively complicated mathematics, as happens in quite a few papers, is intimidating and makes it possible for fundamental errors or inaccurate interpretations of results to go undetected for many years. In addition, sometimes researchers will use the result of an earlier paper as sort of a black box to prove what they want to prove in their own paper without checking the correctness of the earlier mathematical argument. So in this way, an error in one paper can propagate and lead to a large set of fallacious claims. Well, physicians take their Hippocratic oath, committing them to ethical principles. In mathematical sciences, we don't have that. Yet, quasi-mathematical arguments, such as proofs of security, can be misused and can do real harm. And so the last thing I want to mention is that last month I was on Jake Applebaum's PhD committee and took part virtually in his thesis defense at Eindhoven Technical University in the Netherlands. And one thing I was really interested to learn is that the Netherlands have a unique feature of their doctoral defense protocol in that they require all candidates for the PhD to be instructed about scientific integrity. And I'll end by reading briefly from an English translation of the Dutch text that's here. I won't read all of this. It starts, the first promoter has granted you the rights pertaining to the PhD degree, but there are obligations concerning the practice of science too. As a holder of this degree, you are committed to standards of scientific integrity. You have duties towards society. You must be clear about the boundaries of your own expertise, and you must communicate honestly and independently about the results of your work, including potential risks associated with it. Now, wouldn't it be nice if the cryptographic research community adopted a similar set of principles? Okay, thank you very much for your attention. I'll be happy to hear your comments and questions.
And thank you very much, Neal, for your very interesting talk. And do we have any questions from anyone? I might start one while the others think. You mentioned about this, like the tightness gap that you get from analyzing the LPR, and you said that you improved on some of the tightness gaps, and you had a kind of like an improved numerical value, not numerical, but kind of like depending on some parameters. Do you have an estimate for the tightness gap when you put in some kind of standard values into your calculation for the tightness gap, or your improvement for the tightness gap?
Yes, well,
I think this exponent 3 was reduced to like 1/2.
that's right. Yeah, I did give a numerical value choosing certain reasonable values, and that was something like 2 to the 650 for the tightness gap, using our formula and some values. That's certainly not exact, and I doubt very much that we've done the best job that can be done improving the reducing the tightness gap. It could be reduced somewhat further, I'm sure. And other values of parameters could be chosen. If n is chosen large enough, and if you adopt the assumption that the approximate ideal SIVP is exponentially hard, and you adopt the same formulas for exact SIVP to the n/3, then certainly you can choose n large enough so that the tightness gap isn't a problem. But we don't really know how hard this approximate ideal SIVP problem is. So it'd be very, it wouldn't really be a reasonable response to just say, well, let's choose n to be 2,000 or 4,000, and then 2 to the n/3 becomes bigger than the tightness gap. But yeah, there is some flexibility in choosing those exact parameters. There's nothing, unique about what we did, and there's nothing unique about our particular efforts to reduce the tightness gap as much as possible.
So this 2 to the like 600 something figure is with your improved tightness gap, is that right?
Yes. The formula I gave, yes, n to the 20th delta to the -10 was what we got. It was not what would have come directly from using their computation for the Ring-DLWE divergence. Now that was our figure.
I see. Okay, I thought it was directly from the LTR.
No, sorry, no, that was after we did whatever improvements we could make.
I see. Okay. Yeah. Any other questions? Amin, yeah, go ahead.
Yeah, maybe I ask a question. It's Amin from Monash. So in all these like four reasons that you listed, you were always like somehow using Q and N as like examples taken from dilithium or Kyber or Saber, typical examples, right? But something you probably never looked at is the number of samples, right? I think, for example, in Kyber and the most well-known crypto systems that we know, starting from like Regev and like LPR, the one on LPR and now in Kyber, I think that the number of samples there is like restricted, but all those like best known attacks that we know have like, they require a huge number of samples, right? And generally speaking, do you have any comment about the number of samples being used in the crypto systems versus the attacks? And
well, the number of samples, I think usually are roughly in most of the papers are generally of the order roughly big O of n. I don't think they can be much less than n, but they can't be much more than n either, really. There's actually, the number of samples did figure in the tightness gap, but that was one of the terms that I dropped because I don't recall the exact power, but it was to a low power and it would not hugely affect the tightness gap. But we did track the number of samples as one of the parameters. And as I said, those attacks were not necessarily completely realistic attacks, the ones listed by Bernstein and Lange. They were just sort of directions. And of course, there's these Israel Defense Forces, the Matzov paper that was posted last month that has other attacks. But those are not particularly on the ideal lattices. Those are on general lattice problem. But it's not that any of these attacks are breaks. They're not hugely effective. They're just preliminary. And I think perhaps partly because of the existence of these security proofs, that might be one reason why there hasn't been more work done on concrete attacks, because it's kind of discouraging if you think that, well, there's this proof that you can't break it, then why try? But I think more recently there's become more interest, especially when the lattice problems are specialized so much to like cyclotomic ideal and cyclotomic module cases. I think that's already makes it tempting to try some attacks using the number theory. So I think in the future, there are going to be a lot more efforts to attack them than in the past. In the past, the efforts have not been 100% successful, obviously.
Thank you.
Hi. Yeah, hi, Neal. Thank you for the nice talk. Yeah, I'm Ron Steinfeld from Monash. So, yeah, I was going to ask also, did you compare the tightness of these worst case reductions between the unstructured case and the structured case? Is it much worse for the structured one?
Well, it's a little bit hard. There's an earlier paper that that we worked on with Alfred Menezes and a couple other people a few years ago, analyzing that algorithm. It was part of a much larger paper about tightness. And so we didn't go through it in as much detail as the LPR paper. There was a tightness gap of under certain parameters that were reasonable of 2 to the 504th. So superficially speaking, this is a little worse, 2 to the 650, but it's also rough anyway. I wouldn't attach any significance to that. And also it's very possible that a closer examination of the earlier paper would show that there's some tightness gaps that were overlooked. There were a couple things that we came close to overlooking in the LPR paper. It's really, especially, both papers, the regular and the LPR paper, have a lot of steps and a lot of subtleties. So I wouldn't say that the reason for 2 to the 504th versus 2 to the 650 has any great significance. Okay. I'd say they're comparable. They're both very, very high. And the same goes for the paper by Langlois and Stele in the module case. What we found was actually an even bigger tightness gap than in the ring case. But again, a lot has to do with just the details of how the reduction was organized. And so I'm not sure that it's really a hugely important difference in the tightness gaps. The three reductions in the general case, in the ideal case, in the module case, they're all huge, have huge tightness gaps, and I wouldn't be able to say really which is worse.
Mm-hmm. Okay, yeah. Yeah, the other thing that is related to this is, I don't know if you've looked at the documents for the Frodochem NIST submission, because in that document, I think Pikert has given another variant of the worst case reduction. This is for the general lattice case, which he's claiming that it's much tighter than the earlier Regev reduction. So yeah, I was wondering if you had a look at that one to see.
No, thanks for pointing that out. No, I've not seen it. I think we'll have to look carefully at exactly what's being reduced to what.
Yeah, I think it's also reducing to a more special worst case problem. It's not the classical shortest vector problem. Okay. So yeah. Anyway, you may.
Yeah. No, I'm sorry. I'm not familiar with that, but it's sure. Definitely worth looking at. Yeah.
Yeah. Okay. Yeah. Thank you.
All right. I think for the sake of time, we may conclude the session here. Thank you very much, Neal, again, for your very interesting talk. And thank you, everyone, for tuning in. Hope to see you in the next seminar. Thank you.
Thank you. Thank you.